Now today we just continue with the section 1 of chapter 7 and to discuss some properties of Laplace transform. So as we just discussed, the definition of Laplace transform is the integral of a function f of t times e to the negative s t for integrated from 0 to infinity. Okay, so we obtain a function of s for the Laplace transform of this function f. And this is a notation for this Laplace transform, script L bracket function ft. So that means the Laplace transform of this function f. So here are some basic properties of Laplace transforms. We just listed some Laplace transforms of basic functions. So this is an integral transform. So you just do integral of something. So that's an integral transform. So as we already did last time, the Laplace transform of a constant function f of t equals 1. This is 1 of s. So on the right hand side, you should always get the function of s. Okay, as I already said. And you can also take the Laplace transform of t to the n, f of t equals t to the n, and then you just integrate the whole thing with the exponential. And you probably need to do the integration by parts n times. Okay, and at the end, what you get is n factorial over s to n plus 1. Okay, so n is given in the problem itself. So where n is 1, 2, 3, 4, all these natural numbers. And the Laplace transform of e to the at, where a is any real number, that one is pretty straight. If you multiply another exponential e to the negative st and integrate t from 0 to infinity, you can just obtain the result immediately, and that will be 1 over s minus a. Okay. And we can also do Laplace transform of sine function sine kt, where k is a real number constant. And if you do that, you're going to get k over s squared plus k squared. So again, k is a constant. And similarly, you can also find the Laplace transform of cosine kt to be s over s squared plus k squared. And then the Laplace transform of sinh kt is just k over s squared minus k squared. So the difference between sinh and the sine is just plus and minus in the denominator. Okay. And the Laplace transform of cos kt is just s over s squared minus k squared. Okay. So just be a little cautious about the difference between those forms corresponding to different Laplace transforms of those functions. All right, and this can be easily, obtained from the definition. You just carry out the integral, and you get those results. All right. Okay. So let's just do one example by using the results we already had. So let's just find the Laplace transform of a function f. If f is equal to 4t squared minus 5 sine 3t. So according to the definition, you just integrate e to the negative t times ft from 0 to infinity over t. So that's e to the negative st times 40 squared minus 5 sine 3t. Okay, and then you can break up into two integrals and pull out the constant from each integral. So the first integral will be t squared e to the negative st from 0 to infinity, and then you multiply 2 outside. And the other integral is -5 times integral sine 3t times e to the next st from 0 to infinity. And so this just basically, 4 times the Laplace transform t squared. If you still remember the definition of Laplace transform, minus 5 times the Laplace transform sine 3t. Okay, this just shows the Laplace transform is a linear transform. Okay, and then we can use the properties or the results we have on the previous page. So the Laplace transform of t squared is just 2 factorial over s squared s to the 2 plus 1. If you set n equal to 2 in the formula on the last page, you get this. And the Laplace transform of sine 3t, you just let the k equal 3 and use the formula, you get 3 over sine squared plus 3 squared. Okay. So we just simplify the results. 2 factorial is 2, and 4 times 2 is 8. So the first term is 8 over s cubed. 2 plus 1 is 3 in the exponents of the denominator. And the second term is just the -15 5 times 3 over s squared plus 9. 3 squared is 9. So that's the result. Any questions for this simple example? Let's just use the results we already have. Plug in the numbers. If you Laplace transform t to the n and sine kt, let n equal to 2, let k equal to 3. Plug in. If there's no question, let's just move to the next page. All right. Okay. So we just define the Laplace transform. Then the question is, how do we know the Laplace transform exists? We know the Laplace transform is a integral, improper integral. This is the definition. Okay, so to evaluate an improper integral, then we need to use the limit. Okay, remember, you just integrate the whole thing from 0 to some parameter b, and then you take the limit with b approaches infinity. That's how you do improper integrals. So the first step. So this is just the limit, in other words. So the limit can either exist or non-exist. So then we want to know when the limit exists. When does the Laplace transform even exist? So then let's just talk about some sufficient conditions for existence of this Laplace transform. It does not always exist. So the question is, when is it existing? When does the Laplace transform exist? Because if the Laplace transform does not exist, then it does not make any sense to even to find the Laplace transform. Okay, so we need to start from some definition again. So this is about the exponential order. Okay, so what it means by exponential order? A function f is said to be of exponential order if there exists constants c and m, okay, where m is positive, okay. C can be any real numbers, okay. And then some other number t also positive, okay. So we got both m and t positive, such that, okay, with those constants, and then we need this condition to define f, the function to be of exponential order. So when you take the absolute value of this function f, it will be less than or equal to this m times e to the c times capital T, the t. And this is valid for all small t greater than capital T, okay. So what it means is when this variable of the function f, so if you draw the graph of f, okay, you look at the red piece of the curve, t greater than capital T means, all the part of the curve on the right of capital T, okay. So that piece of the curve should be bounded by this function m times e to the ct, okay. So this is a constant, okay. M, C, T, they are all constants. So it essentially means this function has to be bounded by some constant, okay. I think it's e to the small t instead of e to the capital T. I think that I just made the, there was an error in here. It should be c times small t instead of capital T. Okay. So in other words, this function f needs to be bounded by an exponential function. Okay. So if you draw the curve of the function and you draw a curve with the exponential function, the function f should be below the exponential function. So then we call this f is to be of exponential order. Okay, it is bounded by this exponential function. Okay, so again, this should be small t, not capital T. Okay, so then based on this definition, if we know f is of exponential order, then we can say the Laplace transform of the function f will exist. Okay, that's the only thing requirement. Okay, so so here's a statement: if f is piecewise continuous on the interval from 0 to infinity, so it is piece continuous. So if you draw the curve, the graph of the function, it has different pieces, but each piece is continuous. Okay, and of exponential order. Okay, this whole function f is bounded by some exponential function. Okay, then the Laplace transform of the function f exists for s greater than some number c. All right. Okay. So you don't have to worry about this c at this point. It's just some parameter in the theorem, and for any particular function f, you're going to get different as c. Okay. I think we already talked about this before. When we did the Laplace transform of 1 or t or whatever, we did require this s to be positive. Okay, I'll show you later. So that's the whole theorem. And it also says the Laplace transform of this small f, we call it a big F. Okay. So this is just a Laplace transform of small f. We got the function s when we take the Laplace transform, and we call this function capital F of s. And the limit of this capital F as s approaches infinity is 0. Okay. So that's another conclusion from this theorem. Not only the Laplace transform exists, but also the Laplace transform has a limit of 0 as s approaches infinity. Okay. And the only requirement is the function is piecewise continuous and of exponential order. Okay. So you can see whatever I was talking about, when we, did those examples of Laplace transform, we did require this s to be positive, greater than 1, So when we take the limit of this b, when we evaluate the improper integrals, those exponentials will vanish. Okay, so in other words, the Laplace transform exists only for some conditions. This s. Okay, it is function of s, but the s has to be satisfying some conditions. It only works for those s greater than 0, greater than 1, whatever. So you can only define the Laplace transform on these values of s. All right. Okay, so this is the theorem about the sufficient conditions for the existence of the Laplace transform. So let's just do one example, a spatial case of Laplace transform for some, specific functions. In this case, the function f is defined piecewisely. So it's not continuous, but the piecewise continuous. It has two pieces. One piece from 0 to pi, when t is from 0 to pi, you have the function f to be sine t, and the other piece is 0 for t greater than or equal to pi. In other words, if you draw the graph with function, it's just a one piece of the sine function from 0 to pi. Just that. That's the whole thing. Okay. So we want to find the Laplace transform of this function. Obviously, it is piecewisely continuous, and also it's of exponential function. Obviously, this is bounded by any exponential function when they for any m and c, actually. If you draw the graph of exponential functions, goes up or goes down, but it will always bound this piecewise function because the curve is the exponential curve is always on the top of the x-axis, which is the right part of this curve. So this function is bounded by any exponential function. Okay, so it's good. So the Laplace transform should exist. Then let's just evaluate it. Okay, if it does not exist, then there's no point to even start to evaluate the Laplace transform. So according to the definition of the Laplace transform, it's e to negative s t times ft integrating from 0 to infinity. And then because the function is piecewise defined, we can break up the integral into two pieces. One piece integrated from 0 to pi, and the other piece integrated from pi to infinity. And in each piece, we have a different expression for the function f. From 0 to pi, the function f is sine t, and from pi to infinity, the function is 0. So that automatically, makes 0 for the second integral. You integrate 0, you get 0. So that simplifies our situation. So the whole thing is just the integral of e to negative st times sine t from 0 to pi. Okay, and we need to integrate by parts for this integral if you forget. Okay, and we we have to do integral by parts to twice actually. So first, let's just put u equals sine t and dv equals e to negative st dt. If you still remember Calc 2 integral by parts. And then you just find the differential of u, you get the cosine t times dt. Remember, take the derivative of sine t with cosine t. And the integrate e to negative e to the st, you get a v. Okay, so that'd be negative e to the negative st over s. Remember, you have to use substitution with some new variable w equals negative st, and proceed the integration by substitution. You're going to get v equals negative e to the negative st over s. All right. You can easily check that out at home. I'm not going to repeat this in here. It's pretty straightforward. So then when you do the integral of this then we get u times v minus the integral of v du. So this is u dv on the left side. Okay, according to integral parts, it equals uv minus the integral of v du. So u is just sine t, and v is just negative e to the negative st over s, and minus v du. So negative e to the negative st over s times cosine t dt. Okay, integrating from 0 to pi. And you should also evaluate the first term from 0 to pi, subtract actually. So the first term is just negative e to the negative st sine t over s. You pull out the negative sign in the front. And the second term actually becomes plus because there are two negatives. So that's the plus 1 over s integral from 0 to pi e to the negative st times cosine t. You can take out 1 over s from inside the integral because you are integrating over t. So s is just a constant in that sense. Now we need to use the integral parts again to evaluate the integral of e to the negative st cosine t. This time we're going to let u equals cosine t, and the dv equals e to the negative st dt. Okay. So then again, just take the differential of u, get the negative sine t dt. The derivative of cosine t is just negative sine t, and the differential is just the derivative times dt. Okay. And you again, integrate e to the negative st, you get v, which is negative e to the negative st over s. That's the same as we did in the first step here. So once again, I use the formula for integral by parts. Integral of u dv equals uv minus integral of v du. Plug in this uv du dv. So u is cosine t, and v is just negative e to the negative st over s. And v, negative e to the negative st over s, and du. So that's negative sine t dt. So again, you can simplify this, then putting out the negative sign to the front. For the first term, we got negative e to negative st cosine t over s. And this time, the second term has 3 negative signs, so it's still negative. And again, we can also put out the negative, 1 over s to get an integral of e to st sine t. Okay, so if you write down the whole process, the whole thing we did so far, we started from the negative, the integral of e to negative st sine t from 0 to pi, and we just do the first integral by parts. We get the negative e to the negative st sine t over s plus 1 over s times integral of e to negative st cosine t from 0 to pi. And this integral of e to negative st cosine t from 0 to pi, from the second integral by parts, we get that's equal to negative e to the negative st cosine t over s minus 1 over s times the integral of e to the negative st sine t from 0 to pi. So this can be simplified a little bit if you distribute 1 over s in the second part. So the first term is just the same, we don't change, but then we get the second term as negative e to negative st cosine t over s squared. Okay, and the third term becomes a negative 1 over s squared times the integral of e to negative st sine t from 0 to pi. If you just simplify it a little bit. So now we have the integral of e to negative st sine t from 0 to pi on both sides that we can combine. And that's what we need to find actually. So if we move this negative 1 over s squared times the integral of e to negative st sine t from 0 to pi, you get 1 plus 1 over s squared times the integral of e to negative st sine t from 0 to pi. Remember, you factor out the integral, and what is left is just 1 plus 1 over s squared. Okay, so negative will move to the other side, becomes positive. Okay, and then on the right side, you just left with negative e to negative st sine t over s minus e to negative st cosine t over s squared, and both evaluated at pi and 0 and subtract. Okay, and when you do that, this can be easily evaluated. For the first term, when you plug in pi and 0, sine pi and sine 0, they're both 0. So the first term actually vanishes. And the second term, you get cosine pi minus cosine 0. Cosine pi is -1, cosine 0 is 1. So you get what? Actually, you have to plug in pi and 0 for t also. Okay, so when you plug in pi, you get the e to negative s pi times cosine pi over s squared. Cos pi is just -1, but then you get another negative sign, so that becomes positive. So you got the e to negative s pi over s squared positive, and then you subtract this whole thing, plug in 0. Okay. So you minus negative, so that becomes positive. So you plus e to the negative s 0 cosine 0 over s squared when you plug in 0 for t. E to the negative s 0, we know s0 times s times 0 just 0, so e to 0 is 1. And cosine 0 is also 1, so you get 1 over s squared. So so you just get two terms, but both are positive. And if you just rearrange the terms a little bit, put the 1 in the front, you get a 1 plus e to the negative pi s over s squared. Okay, I just wrote the e to the negative s pi as e to the negative pi s. And they're the same. So we got this simple expression. So what you do is just divide 1 plus 1 over s squared on both sides to obtain this integral. And then after some simplification, the whole thing, the answer is just 1 plus e to the negative pi s over s squared plus 1. So we know we have the same denominator s squared. If you divide that, the right hand side by 1 plus 1 over s squared, you can actually, take care of this s squared, both parts, and you get 1 plus e to the negative pi s over s squared plus 1. So that's the integral, which is exactly what the Laplace transform of the original function is. So, so here the final answer. The Laplace transform of the function is just equal to 1 plus e to the negative pi s over s squared plus 1. Okay. So that's the final answer for this example. Any questions for this example? Or any questions for anything in this section?